Okay, so welcome everyone, and thanks for joining today's Target ALS Data Engine workshop. My name is Daniel Wetherill, and I'm a data scientist at Target ALS. And I'll be leading today's session along with a great group of collaborators, Karen Fang and Olex Kozakov from DNAstack, who will be supporting the data portal walkthrough portion of the workshop, as well as Emma Rogi and Kirtana Viraragavan from Verily, who will lead the hands-on analysis portion. So this session is really about walking everyone through the full path of data engine use from data access through to discovery, not just going over where the data lives, but also how to work with it in practice. So this workshop is designed to be hands-on and practical. So we'll combine a live walkthrough with a hands-on component so that by the end, you're not just familiar with the platform, you'll actually have used it. Our goal here is to focus on how to work with the data end to end rather than just describing the system at a high level. So hopefully everyone here should already have access. So today we'll walk you through how to explore the data in the data portal and then how to analyze it using a powerful and accessible cloud computing environment. Will hopefully help drive your discovery. So for the walkthroughs, we're going to try to keep things moving. This session is being recorded. So at the end of the workshop, shortly afterwards, we'll share the recording with everyone here today. So in case anything is missed on the first pass, you can review the recording on your own time. Here's how we'll structure the session. We'll start with a brief introduction to the Target ALS Data Engine, and then we'll move into a live walkthrough where I'll show you how to navigate the portal, understand the data structure and access data sets. And then from there, Emma will help you get oriented in Verily Workbench and walk you through how to set yourself up with your own workspace. And she'll also discuss some key points around cost awareness. Then Kirtana will lead a hands-on example analysis where you'll actually get the chance to run an analysis using actual data. And for these three sections, we'll have everyone here mirror what we're demonstrating so that you can make sure everything works in your own hands and on your own setups. If there are any questions or issues that come up during these walkthroughs, we ask that you please raise the question or within the Q&A panel of this session, if you can raise the question there or upvote somebody else's question or issue. We'll try to field these and pause and address any of the important issues that come up. If you're not familiar, the Q&A panel can be brought up by going down to the bottom of your screen. There's a More button. If you click that, a bunch of buttons should come up and Q&A should be one of those. So then lastly, we'll wrap up with some troubleshooting, a verbal Q&A session, and a bit of a discussion around what analysis pipelines and workflows might be useful for everyone to have as a template within our reference workspace moving forward. So for this last section, if you have anything to say, please just raise your hand and we'll give you the floor to speak. And yeah, so overall, today we're aiming for an interactive, hands-on, and full end-to-end experience. So before we jump into the platform, I wanted to briefly ground us in why this work matters, especially for a group like we have today. We all know ALS remains an incredibly difficult disease. It progresses rapidly, outcomes are still limited, and there's a huge amount of variability across patients, both clinically and at the molecular level. I think what's important and what's changed over the last few years is that the bottleneck isn't really effort anymore. There's no shortage of high quality research or commitment in this field. Instead, the challenge has shifted. We now have growing amounts of data, clinical, genomic, proteomic, often longitudinal, but it's still largely fragmented, hard to integrate and difficult to analyze at scale. So that makes it hard to connect genotype to phenotype or really understand disease progression in a comprehensive way. So at the same time, the opportunity is bigger than it's ever been. There's an emerging large multimodal data sets and the infrastructure to analyze them in scalable, collaborative ways. So the question becomes, how do we actually turn all this data into insight? And that's exactly what the Target ALS Data Engine is designed to enable. So at a high level, the data engine is a unified platform for multimodal ALS research. It brings together two key components. On one end, we have the Target ALS the Target ALS Data Engine portal powered by DNAstack, which is where you access and explore the data. And on the other side, Verily Workbench, which is where you actually analyze the data in a scalable cloud environment. And what makes this platform particularly powerful is that it integrates a wide range of data types, clinical, genomic, transcriptomic, proteomic, and histopathology, and more, all within a single ecosystem. And it's designed to support not just cross-study and cross-modality analysis, but increasingly we're moving towards cross-disease integration as well. In terms of what data is actually available, the platform brings together multimodal data sets across 4 collections. Our global natural history study includes clinical data, whole genome sequencing, both short and long reads sequencing data, multiple proteomics platforms, including TMT mass spec, Olink, and Simoa NFL data, as well as digital health data, including speech, spirometry, and movement signals. Our community-based pop-up study adds clinical and long-read sequencing data tied to environmental exposure data. Our postmortem tissue core includes bulk and spatial RNA-seq, short and long-read whole genome sequencing, as well as histopathology imaging data tied to tissue samples that are accessible through our postmortem tissue core. And the stem cell core includes clinical data along with bulk RNA-seq and short-read whole genome sequencing data, again tied to a small but growing set of stem cell lines that are accessible through the stem cell core. So across these collections, you have access to deep multimodal data sets that can be analyzed both within and hopefully sometime in the future across studies as well. So by the end of this session, our goal is that you feel comfortable navigating and working within this ecosystem. Specifically, you should be able to navigate the data portal, identify data sets relevant to your research, understand how data tables and files are connected through subject, sample, and sequencing type identifiers, access data using cloud-native workflows, and finally run an example analysis in Verily Workbench. So if we can all do that by the end of this session, we'll consider it a success. So I'm going to briefly turn things over to Emma, who will walk everyone through duplicating the demo workspace in Verily Workbench and launching an app, because sometimes these apps take a few minutes to spin up. So we'll let that run in the background while we cover the data portal section of things. So yeah, with that, I'll turn things over to Emma.
Hi, my name is Emma Rogi, and I'm really excited to be here today. Thank you for your time. I will be walking you through first how to duplicate the demo workspace so that you can follow along as we later show you some things in Workbench. So all of you that have Workbench access already, when you log in, please do so using the Login with Google button, which will take you to a page that looks something along the lines of this page, although you may not have quite as many workspaces initially as a newer user. And then you'll want to navigate to this specific URL, which I can put in the chat for this meeting here so that anyone who wants to can just click on that. And if you're logged into Workbench already, you likely will be taken right to this place. So you've been given what's called the reader role on this workspace, which allows you to duplicate it. So I'll give everybody a minute or two to click on that link and be following along with me. But once you're here, in order to duplicate your workspace, which is necessary, again, to follow along today, you're going to want to go to the 3-dot menu here and click Duplicate. And what I would recommend is naming this something slightly different than the original workspace. So in my case, I might put Emma Rogi, my name, in parentheses, and leaving all of this. And so you likely, the pod that you're seeing here is Target ALS GCP. I'll use a different, so I'll show how to find that. ALS GCP should show up for you as an option. And then you'll click Next. In Workbench, policies travel with your data. So since the Target ALS data is subject to a group policy such that anybody that gets access has to be a member of the TALS Data Portal Readers group, you'll note that when you duplicate this workspace, which contains that data, that policy travels with the data in order to ensure governance. So it's letting me know here that there are 3 cloud storage buckets in this workspace, and that when I duplicate it, they will be duplicated as well, which is the intention here so that you have the necessary materials for following along in this webinar. So go ahead and agree to that and say duplicate here. So next, after you've created your workspace and you can distinguish between the parent workspace that we all duplicated and your own, again, because you've put your name here. You go to the Apps tab. So a little bit about workspaces. They're sort of the basic entity within Workbench that we use for organizing both resources and collaborators and compute in the same bundle and kind of access controlling those as one. And so I see we have Javier entering. Okay, great. And so in your demo workspace duplicate, you'll find a lot of information about what is available in this workspace, a lot of links to helpful things such as our support hub documentation. You'll also find resources. So in Workbench, you can have both controlled and referenced resources. So you'll find resources in here, including the demo notebooks we'll go through today. And then in addition, you'll have this, you should navigate to this tab apps. So to create a new app in this instance, and an app is what allows you to perform analysis in your workspace on your workspace resources, including data. You'll click the new app instance. For today's purposes, we will just use a very standard default Jupyter Lab app instance. So no need to change the settings there. You can do all sorts of custom configuration of compute depending on what you're working on. But today we do not need to do that. We can just leave all of these settings as they are at the default and everything will work well. You'll notice here we've got auto stop. This is a really handy feature that prevents you from running up additional expenses when you're not actually using Workbench. So what this means is after your app has been idle for 4 hours, it will automatically be paused, and you will be able to essentially save cost because it won't be running when you don't need it to.
And Emma, just go back for a quick second. I think it's also worth highlighting that if you want to avoid extra data egress fees in working with the data in Verily Workbench, it's important that you choose your zone as US Central 1.
Yes.
We'll go over a little more detail about the cost structure later, but just keep that in mind.
And
Absolutely.
quickly, there's a question around overriding the billing, having issues overriding the billing
Uh,
for
what's the
duplication.
in the context of this duplicating this workspace? What's the exact
Right.
wording of the question?
So Brianna, it seems like you are interested in using a different pod, a different billing than the one that is provided for the webinar. Is that correct?
No, I just might have gotten into the workspace a little bit late before realizing how we duplicate without this missing billing information, but I'm going to go back.
Okay. All right. And we may have time at the end to chat and I can take a look at what you're indicating. Everybody should be using the same billing pod, which is the Target ALS GCP, which has been made available to those of you that already had a Workbench account prior to this webinar. Those of you that don't have access to Workbench yet would not have access to that. So, all right. So, and then this is essentially the default settings. Again, it's really important to avoid unnecessary cost that you have your region be US Central 1A, which is the default here. And then you click next, and then I would name your app something descriptive, something like, maybe webinar app towels, so that you remember what you were using this app for, and hit create app. And it will take between maybe 10 to 15 minutes the first time for your app to spin up, and it will be faster thereafter. So that'll conclude my steps that I'm hoping everyone has followed along with now. And then I'll speak more later about cost optimization and best practices when using Workbench. Are there any questions about the app setup? Has anyone hit a snag or anything that they need assistance with before we continue?
Besides that one major snag that everybody or a lot of people have hit.
So Daniel, I will hand the reins back to you.
Okie doke. Okay, so going over the data portal itself, to find the data portal, if you haven't found it already, you can do a Google search for Target ALS Data Engine, and it should be the first hit that comes up. So I'm going to click on that. And then at the top right, you'll see a button Login. So I'll have everybody click on that. And then I'm going to log in with my Google-enabled institutional email address. And again, hopefully everybody here already has access to the data portal. If not, again, please just listen. And again, we'll be sharing the recording after the workshop so you can follow along later on. So when we get into the data portal, this is the landing page. It lists all the different data collections. I've mentioned four of these collections. There's a fifth here. This is an amalgamation of all of the long-read sequencing data that we have across three of our other collections. This extra collection just gives some additional variant annotation data related to those long-read sequencing files. So for today, we will be using the Global Natural History Study collection. So we can access this collection by clicking on the descriptive tab there. So have everybody do that. And this will bring us to an overview tab for this collection. Every collection has this overview tab. It just gives a brief description of the data collection, what's in there, as well as a link to download data dictionaries for all the different data tables that are contained within the collection. There's also links to method sections describing how the data was collected, and also in this collections case, links to some files describing the files associated with short read and long read whole genome sequencing and what they can be used for. There's also, each collection has this link to download a document that gives some information about controlled abbreviations that are used throughout the collections, gene symbols used, and missingness codes. I'll go over the missingness codes in a bit here. Also, then you'll see this little blurb that includes a link to Verily Workbench, as well as our user manual and a demo video. Both of these, the user manual is being updated, so we will provide a link to the updated user manual shortly after this workshop. The demo video is also a little bit out of date. We're working to update that as well. There's also this link to a shell script that can be used for downloading files in batch mode. So we'll get to this in a little bit, but I'll have everybody just click on this link for now so that we all download that script. And then next, you'll see some data visualizations that provide some kind of high-level overview of summary statistics describing the data in the collection. And then if we look back up the top of the page, at this within the header here, you'll see several different tabs for all of the various different data tables within the collection. Some of our collections are larger than others, so in some cases, you might have to extend your browser window a little bit to reveal more tab. That's a drop-down that allows you to navigate to any remaining tables there's no room to display. So for today, we're all going to click on clinical data. That will take us into Explorer mode so we can explore this particular table. First thing I'll show you is there's this button here that can be pressed to hide or show the filtering features that can be used to filter the table. So let's just hide those for now. If we click on this columns drop down, well, let me first describe what we're seeing here. So here's the data table itself, showing some of the columns within the table. They're not all visible all at once, so you can see the rest of the columns by scrolling left or right. And then all the rows of data similarly aren't all able to be displayed at once, so you can scroll up or down to look at those. Down here, we have a drop down that allows us to select how many rows of data are displayed per page, and let's just go down to 500 for now. And then you can navigate page to page down here. So additionally, there's this column drop down that you can use to view all the different columns in this particular table. You can toggle toggle various columns on or off, which will hide or show them in your display. And you can also click on this button here to rearrange how the columns are displayed to your liking, so you can visualize things a little bit better. Let's now all click on this button here and bring back the filter function. So I'm just going to go over in detail how to use these filters. And so for each of the columns in the table, each of these columns has its own filter. And so let's demonstrate how to filter using the subject ID column. So you can access the filter functionality by clicking the plus button. And now I'm going to highlight one of the subjects and copy that and paste it into the subject ID filter field. And just be careful not to copy in any leading or trailing white spaces, just to demonstrate if I have a trailing white space here, no search results come up. So let me try that again without the trailing white space. The reason for that is when you're searching within the text-based columns, it's searching for an exact match. So you need to make sure that that what you're putting in there is an exact match to what you're looking for. So I'm going to hit the apply button, and that's filtered the number of rows that are visible. So now we just see the 2 rows of data for this particular subject. It's a non-neurological control for the natural history study. Our controls come in for 2 visits separated by a year. The ALS subjects come in for up to 5 visits separated by 4 months. So yeah, this makes sense and is looking correct. All of the filters that you've applied are described here in this applied filter section, and you can remove specific filters or clear them all by clicking those 2 buttons. And in addition to being able to filter for rows that contain just a specific value, you can also, in the case of columns that contain text data, you can search for substrings. So let me just grab a substring of this subject ID. And the way we do that is by toggling on the has functionality. So unlike the standard filtration mode, which looks for exact values, when you toggle has on, it's going to look for substrings within larger strings. When I hit apply, now we can see this subject we captured before is still there, as well as another subject. They all start with NUAD. Similarly, you can exclude values that are being displayed, and I'll demonstrate this with the clinical group column. To do this, we use the not function. So here I'll copy that and paste this in, and I'm going to exclude non-neurological controls by hitting apply. Now all we see are the rows of data from ALS subjects. Now this column, like the standard filter mode this filter, like the standard filter mode, requires an exact match. So if I just put in control, or if I put not control and apply, the filter doesn't work. So just bear that in mind. Let's see, we can also take advantage of regular expressions to do more complicated search patterns. So I'm just going to grab this regular expression here, go back to the subject ID filter, and make sure that I toggle the rejects mode on. And so here I'm searching for all subject IDs that match this following pattern, starting with any U, then any 7 characters, and ending with F. So let me hit apply. And sure enough, I've got all of the hits that match that pattern. We can also apply multiple filters at the same time. So I can also filter for all of the rows of data that are from ALS subjects within that subset that's coming up. And so yeah, here we've excluded the 2 controls. And yeah, so I think that, oh no, let me just go over a few more things. So that's for filtering in text-based columns. There's also numerical data columns. So we will just demonstrate how a couple extra functionalities specific to numerical data. So for using the visit number column here, let's just clear these. There's also the ability to search for all values below or equal to 3 by using the max functionality. So when I apply that, now we're only seeing rows of data from visits 1, 2, and 3. We don't see any 4s or 5s. Similarly, you can do the opposite and look for 3 and up by using the min functionality. Now we just have 3, 4s, and 5s. And lastly, you can use the between function to search for everything between 2. When I type a space, it automatically fills in and. So I'm going to add 2 and 4. And we should exclude all data from rows 1 and 5. So that's how that works. Now, I mentioned earlier that we have missingness codes within the data. I bring this up because you may have also noticed there's the ability to filter for all rows that are empty or not empty within a certain column. These 2 functions shouldn't come up too often in these tables because we make an effort to not have any empty values within columns. If there's missing data within a column, we fill it with a missingness code, which provides information about why that data is missing. So for the missingness codes, within text-based data, an example of a missingness code would be n/a for not applicable. If something's not applicable in a numerical data column, the code would be -888. So all of our numerical missingness codes are large negative integers that shouldn't come up within that column. So just be mindful to remove those placeholder missingness sentinels before analyzing the data. All right, so let me just filter this once more here by subject. So once you've filtered your data or not filtered your data, a lot of you might be interested in downloading the data, this tabular data, to your local computer to be able to work with it offline. So I'm going to just show everybody here how to do that. So these data tables are downloaded as CSVs by clicking on the Export to CSV button. This drop-down will reveal 3 different ways of exporting to CSV. First thing I'll show you is the ability to export selected rows. So we can select specific rows of data by clicking the box next to that row, or you can select all data that's presently viewable by selecting the box in the header. But let's just start with one of the rows. If I click on Export to CSV and then Export Selected Rows, we can see that I've got a new CSV file in my download folder. So let's open that, and you can see that, yeah, there's just that one row of data that's present. Similarly, if I select both rows or just select all in the header here, and then export selected rows, now I should have 2 rows of data. Let's just confirm that. All right, that seems to be the case. So if you want to download all rows of data that are presently visible, there's 2 ways of doing that, the way I just showed you by selecting all and then clicking export selected rows. Or if nothing is selected, you can accomplish the same thing by clicking on export page. And let's just peek at that and see, yeah, we've got both visible rows there. Lastly, if you're interested in downloading all of the data with, all of the data in general, unfiltered or filtered, you can do that by clicking export to CSV and then clicking on export all via CLI. And so this, let's see, to demonstrate this, let's remove this filter. There's 502 rows of data in this table. So not all of them are visible. I just have 500 rows visible. But if I go to export all via CLI, you'll have to have installed the DNAstack CLI and library package in order to do this. If you haven't done this already, you can click on this link command line interface. That will take you to the DNAstack documentation page where you can find installation instructions for the command line interface tools. Explains how to install Python. If you scroll down, you can see the instructions for installing these tools. So hopefully most of you have already done that. So I'm going to demonstrate how to do this, and you can feel free to follow along. You can copy this command by either selecting it and hitting Command C, or you can copy it by simply clicking copy to clipboard. I can then go over to a shell session and paste that command in. And let me just clean up my download folder. When I do that, a new file appears in my downloads folder, and I'm going to open that to confirm that all the data is there. So now we can see that there is indeed 502 rows of data that was downloaded. So that's all of the data. If I had a filter applied, let's filter by clinical group for just ALS patients, and then I export all via CLI, it's going to just include those filtered rows. So here we should have less than 502 rows of data, which is indeed the case. All right, so additionally, there's this view query button, which can be used to query the filtered data or all of the data. So let's remove this filter for now. And if we click view query, this pop-up window comes up showing a command line command, Python code, or a raw SQL query that can be used to query this data table. And you may notice that the Python code is basically a wrapper containing this SQL query. Same with the command line interface command. And for those of you who are familiar with SQL querying, you'll note that right now we're querying all of rows of data in all columns. So I can, well, actually, let me just cut that down a little bit by, yeah, let's try it by clinical group. When I apply a filter and then view query, now you'll notice that the SQL query wrapped in the CLI command contains an additional bit of language that limits the query to just those rows that contain ALS within the clinical group column. So now if I copy that and paste it into my, oops. Yeah. And paste that into my shell console and execute it, it should list all those rows of data, all of the ALS rows of data only in JSON format. And for those of you who are familiar with SQL querying, you can customize the query within that wrapper by just replacing everything between these two quotes here. So I've done that with this query here. So this is just an example of a custom query that I've thrown in that will display all subject IDs that are present in all three of the clinical data, whole genome sequencing metadata, and mass spec proteomics data table. So when I execute that, it lists all of the subject IDs that are found within all three of these tables. So that's a handy little thing to know. The last thing, so yeah, so far we've covered how to view and download.
Can I ask a question?
Oh, yes, please go ahead.
Hey, sorry, yeah, John Kipanok here. So just yeah, thank you. It's very helpful. But I've tried to do what you said. I got through the security, entered my code, and then I got another error. It said just no grant for requested audience or something, or failed to perform client credential authentication. Is that server response with HTTP 400? Is that, but everything worked up until, you know, what I mean, I went through, logged in, did the security code, entered the key code, etc.
Um, I believe the first time you run it, you have to, Olex, can you weigh in on this? I think you have to validate your session.
I did that. That
Okay,
all worked. I
that
did
all
that,
worked.
entered the code, it got that. That all worked fine. But then I got another error, which is I've put it in the chat as well. Sorry if I'm just dragging it off, ignore me. But like but it would just be it's a really obviously be helpful to get this solved now.
Yeah, yeah. So Olex, if you can just take a look at that
I'll
error
put the
message.
snippet in the chat. Give me a sec.
Yeah, I'll just keep going. Olex, cut me off when you've got an answer to this question, and we'll circle back to it in a minute. Okay, so yeah, in addition to these tabular data on the data engine, we also provide raw and somewhat curated data files that are non-tabular. So to access those, all of our collections have some of these files, and therefore each of the collections within the data portal will contain a table called blank data files, for instance, sequencing data files. This table will list all of the sequencing data files that we have associated with this collection, along with some useful metadata associated with all those data files, including subject ID, clinical group, sample ID, etc. Also file type, and the last column is ingestion date. This can be handy if you want to filter for just those files that have been uploaded since you've last downloaded the files. So let me just filter this a little bit. So I'm going to do a reject search within subject ID. Let's say I have two subjects of interest that I'm interested in downloading files for. I can do a reject search for this subject or this subject. Hit apply. And now I just have sequencing data files for those two subjects. You'll notice in the sequencing type column that these files include short read and long read data. So let's say I'm just interested in short read. So let me filter for just those files. Now, all we have left in this table are short read files. And then let's say I only want a specific file type. A lot of you will be interested in the aligned sequences. So for that, we will filter for file type, and I'll do a reject search for BAM or CRAM. We've got both, depending on the subject. And I'll hit apply, and now we can see that there's two CRAM files associated with these two subjects. Now, for the purpose of this demonstration, it'll take too long to download those BAM files. They're quite large, or CRAM files. So I'm going to swap this out for another reject search for MD5 or text files. Now we just have rows of text and MD5 files. So we can then, if you're just interested in downloading one file, you can select this path to that file. It's stored within a Google Cloud Storage bucket. And just to go over cost a little bit here, I think it's a good point to talk, a good point to talk over it. The Google Cloud Storage buckets are requester pays. So that means if you want to download the data and use it locally, you'll have to pay egress fees associated with that download. And if you're interested in understanding egress fees, there's documentation on the Google Cloud pages on that. And so this can be a more cost-effective way of analyzing the data in certain situations. For instance, if you're just working with relatively few small-sized files, it could be potentially more cost-effective to just download the data directly onto your local computer and work with it there. In other cases, for instance, if you're working with a lot of large files, it might make more sense from a cost perspective to work with the data in Verily Workbench, where, as we alluded to earlier, if you've set your workspaces up correctly in the US Central 1 zone, you can avoid those egress fees because the data, the virtual machines that you're running the analysis on are located within that same region, so there's no egress happening. So you can avoid those egress fees. Verily Workbench has a pay-as-you-go cost structure. So depending on how long their analysis is running and what kind of computational resources you need, that will be more or less. But yeah, still in a lot of cases, it can be more cost effective to run your analyses on Verily Workbench. Another reason you might want to run the analysis on Verily Workbench versus your own local computer is just time. A lot of people don't have access on their local computers to the same kind of computational resources that are available through cloud computing. So that's another reason to do it there. But anyway, so to demonstrate how to download a file locally, if that's the way you want to go, you can copy the address there. And here I've got the generic command that is used to download these files. And to execute this command, you need to have Google Cloud CLI tools previously installed. Again, hopefully a lot of you have already done that. If you haven't, it's outlined pretty well in the user manual that I provided everybody with. You will need to activate within Google Cloud CLI tools. There's an ability to activate your current account to the email address that you're currently working with within the data engine. Once you've done that, you can also link billing information to that account, and that's done through a project ID. So to run this command, again, because it's requester pays, you'll need to have a project ID entered within the billing project flag. You can replace this generic term with the source path that we just copied over, and then you can specify a destination path on your local computer where you want it to download to. So I've just set up this example download for us here. I'm going to just run it just to demonstrate that this works. So yeah, well, you can see that the download completed and MD5 file is now in my downloads folder. So that's great if you just want to download one or two files, but if you wanted to download hundreds of files or more, that would be very tedious to run that one by one. So I'll just show everybody how to instigate batch downloads. So we can do what I showed you earlier. We can select all the rows that are visible, export to CSV these selected rows, and now there's a new CSV file in my download folder, which contains these 44 rows of data. Just to streamline this even more, I'm going to reduce this down to 3 files and save this. Now, this batch download shell script that I had everybody download comes into play. So before we can use this script, we will need to give it the right permissions. So we do this by typing shmod plus small x and then the name of the file. So everybody can follow along and do this. Once we've given the necessary permissions, we can run the file, and you'll need to be within the directory that this shell script is located. Then you can type dot backslash and then batch underscore download sh space, and then either just the name of the file if this CSV file is in the same directory as the batch download shell script. Otherwise, you'll need to paste in the path to this file. When I hit enter, it's going to ask me for my project ID, which I will type in here now. And if I have done that correctly, it will start downloading, and which it's doing, and it'll give me a little message, all files processed, let me know that the downloads are complete. And we should see 3 files in the download folder, in the downloads folder, which is indeed the case. So yeah, that concludes everything that you need to know about navigating and downloading data directly from the data portal. I will now pass things over to Emma again, who will explain how to work with this data in Verily Workbench, if that's how you're interested in working with it.
Maybe just a small pause. Are people following along? Any questions? Should we give you a minute to catch up?
So I noticed somebody asking if we can see how much those downloads will cost. Yeah, it's very easy to estimate. If you go to the Google Cloud documentation page, there's a page that lays out pretty clearly what the fees are for downloading the data, and it's by gigabyte, and so you can, if you within those sequencing data files table, one of the columns of data is the file size, so you can sum across all rows of data within that column, and you'll get an idea of how many gigabytes of data you're downloading. And I think it's about 12 cents a gigabyte, if I recall. Yeah, I think depending on.
Oh, sorry.
Go ahead, Emma.
We'll be computing that actually shortly in my notebook too. So you'll have another opportunity to kind of learn more about that. Daniel's totally correct that the source of all truth should always be the GCP site with the pricing. But the notebook that I'm about to show you will also walk you through kind of estimating cost for localizing particular data. So we'll talk about that as well. So hopefully everyone can see my screen. I was introduced earlier. My name is Emma. I'm a Workbench solutions engineer. And I'm going to be going through a little bit about Workbench, how to use Workbench, how to access your data on Workbench, and how to optimize your costs on Workbench. But before I discuss those things, I wanted to mention a few reasons that you might want to use Workbench. So one reason is that there is data discovery and exploration available. Not just the Target ALS data is available on Workbench, but other data that you may wish to co-analyze with it. And it is safe and in a secure, trusted research environment when it's in Workbench with all of the data governance built in. As I mentioned earlier, in Workbench, policies follow your data. And so you can feel secure when you're working with Target ALS data in Workbench that you are doing so in compliance with Target ALS policies and the data use agreement. In addition, Workbench is collaborative. You can share a workspace with your collaborators. You can then view their artifacts, their visualizations. It's really effective for working with others, but remaining, again, in that trusted research environment. And I think hopefully you'll have an additional reason to use Workbench after this webinar, which is that you now have seen it in action and have ideas about how you might use it yourself. So Workbench sort of brings together these concepts of infrastructure, because we support multiple clouds, including Google Cloud and AWS, users, and all of the things that users want to be able to do to analyze their data in Workbench, and tools. And so the application that we started up earlier, our default Jupyter app, comes pre-installed with a number of tools that we will talk about today. So hopefully those of you who have access have already logged into Workbench. And I will now be moving to that workspace that we together duplicated and to the Workbench app that we created, which is the default Jupyter Lab app. So in this workspace, you will find that you have 2 directories on your app when you first open it. And again, to open your app, you would go to the apps, and then you can click on this and open it. You'll see that you have a repos directory, which is for if you've configured our GitHub SSH key. 2 best practices that we always emphasize in Workbench are to use source control and to back up any important files that you have to a workspace controlled bucket. We talked a little bit briefly earlier about resources and what they mean in Workbench. There are 2 primary types of resources. The first kind is a referenced resource, which means you have a pointer to a resource that lives outside of Workbench, and you are referencing that. And the other kind is called a controlled resource, and that means that if you were to delete the resource in your workspace, it would be gone. The kind that we're suggesting users have in their own personal workspaces is a controlled bucket, a controlled Google Cloud Storage bucket for their data and for any sort of intermediate outputs they may wish to preserve. And we'll talk a little bit about why that is. Something handy in Workbench is that you can actually preview your resources. Even if you haven't gotten an app spun up, you can still do this as long as you've duplicated the workspace. You can click on any of these folders here, which each represent a bucket, and you can browse the contents of that bucket. And so, for example, let's take a look at some of the data that we're going to be working with Kirchner later. She'll be working with this data with you. This is a CSV file. We are able to preview this CSV file, take a look at what is in there, whether that looks correct to us. And if I have a collaborator, say Daniel, and I want him to take a look at this CSV file as well, I can share my workspace with him and then send him this preview link, and then it will take him directly to this preview. So I can say, Daniel, I would like you to look at this CSV and let me know if you think it looks fine, and he can do so. In addition to CSV files, we also can preview notebooks. So we'll take a look quickly at the notebook that I'm planning to work through with you. I have an HTML version in the bucket so that you can see it with all the outputs. And then I also have a version, obviously, without those outputs that you'll be seeing. So if we were to preview this, we'll be able to see the notebook that we're about to run together. Taking a moment. Great. And so you can see that the main scope of this notebook will be some basic environment setup that we're doing for some dependencies. We'll be creating our own kernel for running the notebook. And then we'll be looking at the workspace context. We'll be pulling in some data and localizing it. And as promised, we'll be calculating the size and therefore cost of some data. And this should give you a good framework for figuring out costs yourself in the future if you wish to basically localize some of your data to a GCS bucket, ideally within the same region. So let's get started with that. So I will go to my application. And so again, you'll see that you have the repos and workspace directory when you first open your application. The repos directory is for any GitHub repositories you may have once you've set up the GitHub integration. The workspace directory is going to map, it's basically those 3 workspace controlled buckets are then mounted on your application, which is really nice. So if we were to navigate to here in this directory with the webinar demo notebooks and open up the version of this notebook that has the outputs, we'll do, for example, you can see that this is that fully executed notebook with all of the outputs. In addition, if we were to look at the notebook without the outputs, we can see here that it hasn't been executed yet. What I'm going to do before I run this notebook is open a terminal. And the reason for that is that I am currently working in this workspace, not in my duplicate workspace. And for all of you to have the correct copy of this demo notebook, which has no cells executed, I actually need to make a copy of it outside of my bucket because this bucket is syncing. So if I were to delete any of these files from this bucket in the parent workspace, they wouldn't be available to you when you would duplicate this, say, in the future. So I'm going to copy from this directory my Getting Started notebook I can copy it to the home directory, which is just tilde and then a slash. Or I could, if I had a Git repo set up, I could run the same command and copy it to repos, and then, whatever the name of my repo is. But we'll just copy it to the main directory this time. Okay, so then we can navigate here in the file browser to my notebook, copy right here. I'm going to close these other ones just to make sure we're running the right one. Great. Okay, and so today we'll be going through a few different concepts. The first concept is this environment setup. So we're going to need some tools and dependencies, including the DNAstack client library, in order to run this notebook and pull in the data. So on your first time, when you're running this notebook, you'll want to copy these commands and actually go ahead and run those in your terminal. Let me see. I'm copying. Okay, great. So I'm going to run these commands. And so you'll see that the steps we're taking here are to use Conda, which is a Python package manager that comes pre-installed on your Workbench app, to install DNAstack and then create basically a virtual environment that includes the right kind of Python for the DNAstack client library. And that's really important because if we don't do this, then the DNAstack client will not have the right version of Python. So this will take a minute or two. And again, it will take a longer time the first time you run this, but thereafter it's pretty fast. You'll see that we're installing some other dependencies here. And then the final step here is that in order for our notebook to use as its runtime the right version of Python that has the DNAstack client app, we have to create what's called a kernel. And so that's what this last step does, number 4. And we're going to name it Python 3.1 DNAstack so that we know exactly which one it is. So I have actually already created this. So you can see that it is listed here in my options. Once you've created your kernel, you will go to this top right corner and click on your version, whichever one that is, and you'll see you have a whole list. But the one that you actually want for the Getting Started cost optimization notebook is this Python 3.11 DNAstack. So let's see where we are here. Okay, great. So we have succeeded with our installation here. And so now we can go ahead and run this cell right here, which is going to validate the fact that we have installed everything properly. And if you see this green check mark, then you are in good stead to continue to the next cell. Another neat thing about Workbench is that because it is cloud agnostic, but built on top of the cloud, you have the ability to reference certain environment variables for your workspace. So in this case, we'll be accessing some data, and we will need to specify the bucket name in our workspace. And since I'm not the owner of your workspace, which is a duplicate of this, I don't have your workspace project ID. But your workspace project app itself does have that information. And so what this cell is doing is basically saving that variable so we can use it later when we're doing operations like saving data to a bucket in the workspace. And so this will take a second to run, and then we'll see it print out something, my GCP project ID, as well as the ID of that workspace bucket. So as you can see, now we've got the GCP project ID, which is WBBD-corn 3083. And then I also have the workspace bucket ID. The next step in the following cell, we're going to actually initialize the DNAstack Data Connect client, which is how we can authenticate and pull data directly from the data engine. Okay, and so then next, when the DNAstack Connect client is connected, the results are going to be in this results iterator. So we're just going to take a look at those and validate that they look good in the data frame. And in fact, they do. This is as we expect it. So there are a couple of different ways you can think through localizing data when working in Workbench. Daniel hit on the most important one earlier, which is that to avoid unnecessary cost, it's important to keep the data in the same region, which is US Central 1. If you're only working with data for a short amount of time, one option that you have is to simply localize your data to your app's file system. And so you can do that with commands like the ones I'm just now running. I'm saving this CSV file that we pulled in from the Data Connect client, or via the Data Connect client from Data Engine, to a CSV file in my local workspace. And we can see that when I ran that command, it actually, in fact, did so, because we can click on this and open it and see that it is a CSV file that has all that data that we were previewing in the previous cell. This is a good option for, again, short term. Perhaps if you want to take a look at something before running a larger job on that particular resource. However, for anything, it's important to remember that when your app is stopped, you're still being charged for disk, but you're not being charged for compute. So let's say your app goes to sleep after 4 hours of inactivity. Any data on that app should be preserved. Restarting the app will bring that data back, and your file system will come back in the same state. However, if the app is deleted, or if something about the app becomes corrupted at some point, that data can be lost. So it's not what we would recommend for medium to long-term strategy at all. It is handy while you're actively working with the data, but we actually think that it's a best practice to localize data to your workspace controlled GCS bucket for anything that you plan to reference or utilize in the future, really. So this is using that workspace bucket parameter that we set up earlier. And you'll see that I'm running a gcloud command here, basically, that it's going to populate this with the ID of my workspace bucket, and it's going to save that same CSV to that bucket. All right, and so now we come to the thorny topic of cloud costs. How can we minimize those? And the basis of that is to understand your data, understand how much data you are working with. And so earlier we set the GCP project ID value. Today we'll look at the TALS Columbia postmortem tissue data. And in this particular example, which is based on a real one from a researcher that wrote to me about this, we are excluding BAM and .cl cloop files. We want only the files in the bucket that are not those files. So you could take a look at this and kind of extrapolate it to your own needs, depending on which file types you want to include or exclude. And we're setting our target bucket to the bucket here. We're going to get the total bucket size first, which we can do with this command. And so we're getting this total bucket size. Then we're going to list all the files in a temp file to see exactly how many files are in there. And since in this particular example, we're looking for only certain file types, not the BAMs or the .cloops, we will take the chance to then calculate exactly how many of the files that meet our specific criteria we need. Great, and so now we have a good estimate. We know that it's going to be somewhere around these amount of sizes for these particular files that are being excluded. We know that it's going to be this many bytes for the ones that are remaining included. And so now we can talk a little bit about pricing. You can update this notebook with your own real rates from your own cloud billing or contract pricing. They are currently in US dollars per gigabyte per month. It's important to understand, and this is really well documented in our support hub docs, so I definitely recommend checking those out for a more thorough overview. Which activities in Workbench are going to generate charge? Creating a workspace, adding a bucket, neither of those actually creates charge. It's when you begin to add data that you do accrue some cost there, or using a cloud app. And so we do provide a lot of resources on how to estimate the cost of those. And then if you're going to localize data from a bucket to your own environment outside of Workbench, whether that's your laptop or an HPC, maybe your university has an HPC, something like that, that does generally accrue some charges. We like to use the phrase that those charges are typically small for small amounts of data, but can be very large for large amounts of data. So again, make sure you understand the amount of data you're working with, and then you can answer questions about how much it will probably cost. As best practices, it's really important to avoid kind of double billing. So a lot of the TALS data is located in addition to in the data engine, in requester pays buckets. The best practices for working with those are to localize only once. If you plan to read a file several times or use it for several purposes, it's much cheaper to copy it once to your own workspace bucket than it is to read it repeatedly. Subsequent reads are free within the same region, so keep that in mind. So in this cell here, I've imputed the pricing information that my cloud billing costs, and I'm going to print basically this pricing. And then I'm going to show you in the next section how to estimate the cost of localizing some of the data from the Data Connect results that we found earlier to a workspace bucket. So there's an explanation of how this works here. And so we've set up egress cost calculators for both the premium and standard tier. And then this cell calculates your cost. So in this particular case, it looks like if I have standard tier, my cost breakdown is going to be about $5.80. That's not terrible. If I have premium tier, it's going to be about $8.19. I also included a scenario where I'm transferring the data to a different region, just for an example that you could repurpose. And so there is a small cost there. In addition, this cell produces a table that shows you kind of egress costs at different data sizes for quick budgeting. So if you know roughly your data size and you know you're not going to leave the region, or you know you are going to leave the region, generally this is probably a handy tool to kind of give you a ballpark estimate of your lower and upper bounds. All right, and so I've also left off with a checklist, basically things to think through before you localize your data. And with that, I will end my section and hand the torch to Kirtana, unless there are any billing specific questions at this time. Running these notebooks today should not be very costly for any of you.
Okay, if there are no questions, then we can go ahead and move on. I don't see any questions in the chat and I don't see any hand raised. I would like, if those of you who have Workbench access and have your app open and have been following along, to navigate to this notebook. It'll be the stem cell RNA-seq annotated notebook. If it is in your workspace right now and you've not copied it over, feel free to follow this command to copy over the notebooks from the webinar demo notebooks folder into your repos folder. Once you've done that, we can just start going over this. So this is a brief introduction to what is referred to as bulk RNA-seq analysis. And for the sake of today's demonstration, we will be going over the stem cell core data that is available in the Target ALS portal. This is a data set from 8 samples from 4 subjects that include ALS data and non-neurological control data, and has about 60,664 genes. And the goal of this type of analysis is to look at ALS versus control. We can also look at iPSC versus the motor neuron cells to see if there are any differentiation effects. And look at the interaction and see if ALS-specific genes actually emerge or amplify cell differentiation. I see that there are a few hands up in the chat. So the first thing we're going to do is install. We're going to make sure that actually we are back to our Python Conda environment Jupyter. So if you're currently in the Conda environment that you had set up before, go ahead and switch and revert to that environment. We're first going to run the installation steps for some recommended packages. If this is the first time that you will be running this notebook, this step may take a while as it installs a few packages that we may need. That includes PyDESeq2, which is the key package that we will need to do the DEG analysis. Once we have done that, we can go ahead and actually run our cell to do the import steps. You will see that it's importing all of the packages and that we're also setting some genes. So these currently are listing for some key ALS genes that we would be interested in looking at. Feel free to go back and turn to this notebook if you are interested in looking at different gene sets, if you are interested in doing different kind of analyses with different sets of data. This is a template notebook, and hopefully the goal is that, through this webinar, you know how to interact with the DNAstack portal and you know how to pull different data sets from the portal, and so you can work with that. The next thing we're going to do is we're going to read in our count CSV as well as our metadata CSV. These have been tabulated and populated in this workspace for you, so you can go ahead and run this cell. You should see something that looks like this. You should have a counts table with about 485,000 rows and 6 columns, as well as a metadata table with 8 rows and 13 columns. We're going to skip this second option because, as Emma mentioned, the best practice is to actually localize your data files and then upload them to the GCS bucket. Should you want to stream it directly from the bucket itself, this is an option for you. We're then going to reshape our count matrix. So this reformats it into a shape that will be pivotal for doing our downstream analysis. And so once you run this cell, you can see that it has basically converted it into a table with 8 samples or 8 rows and 60,664 genes. And we can also see a brief breakdown of the conditions as well as the cell types. The first step, once we have obtained the data in any analysis, is to do what's called quality control, or QC, and compare the metrics and plot them side by side. So first, what you're going to do, this is also just a best practice step, is in your current repository, you will want to create what's called an output folder. This exclamation mark is a way in Jupyter Notebook, if you're not familiar, to basically run the equivalent of a command line. So in my case, it cannot make the directory because it already exists. But in your case, you should be able to create this output folder. And this is where you can save, should you wish, any plots, CSVs that you generate, etc. So we're going to first run this QC metric cell. And you can see that we have created a few bar plots for us to examine our data and look at them by library size as well as the number of genes that are detected. And it's differentiated by cell type, control versus ALS, as well as the diagnosis, control versus ALS, as well as the cell type, iPSC versus motor neuron. The next step we're going to do is do what's called a log CPM normalization. Raw counts cannot be compared directly between the samples since each of them has a different library size. Some have generated more reads than others, and the normalization removes this technical bias. And this will allow us to compare everything as one. Once we've done that, we'll do what's called a PCA, or sample clustering. So principal component analysis is a dimensionality reduction technique. So right now our data has about 60,000 genes. PCA intends to find the maximum variance and projects each sample down to just a few numbers. So essentially we want to identify principal components that basically capture most of the biological system. Since most genes don't really vary between samples, they add what's referred to as noise, without necessarily adding information. So we will select the most variable genes and focus the PCA on those. So what we really expect is we have 5 components, and you can see about 70% of the variance is explained in the first few, and then 11, and then 7. We can plot, just to get a better idea, what these PCAs look like. So you can see that we've done a PCA by cell type and color and diagnosis. And they seem to cluster, for the most part, pretty well. So we can see that our motor neurons cluster on the right, our controls seem to cluster on the left, and we can see that there's also ALS that seem to cluster, up to the top. And we really expect to see our scree plot to look like this, with this curvature showing that once again 70% of the variance is calculated in the first principal component that we clustered. This is a good sign that our data is actually, pretty clean. We're then going to do what's called hierarchical clustering heat map. And so what this does is it does a few statistical calculations, and we can group our samples and our genes, which are our columns and our rows, by similarity. So we have this lovely heat plot, and we can see that they do cluster, as we would expect to see. iPSCs and motor neurons tend to cluster in different parts, and our ALS and our control also seems to cluster together. The next step is obtaining what's called annotations. So our count matrix, as you can see, uses what's called our ensemble IDs, which have this ENSG identifier at the beginning, since that's what alignment software produces. Biologically, we are most familiar with what's called gene symbols like SOD1, TDAT, etc. So MyGene is a Python client that provides comprehensive gene annotations for all human genes and queries the database. If you want to run this by yourself, you will run this command to install MyGene. However, we have already, for the sake of time, this step, since there are 60,000 genes, does take quite a bit of time. We have populated the gene annotations in the CSV file that Emma actually previewed for you earlier. So you can run this kernel, and we can bypass it since we have found that we have those cached CSVs. And we will want to extract the ALS and control profiles for those genes. So if you recall at the beginning, we were interested in looking at about 15 ALS genes. So we have just obtained the gene expression and the annotations and saved them. With this, we can generate what's referred to an ALS heat map. So once again, we're looking at the expression profile of our selected genes based on their cell type and diagnosis. If you're interested, you can also plot the expression of genes by themselves. So this is SOD1, TAR-DBP. Feel free to go back to this cell and change those genes if there is a particular gene of interest for you. Our next step, and this is probably the key step, is what's called differential expression analysis using something called a DESeq2. We will run this even though we only have 8 samples. Just keep in mind, if you recall from high school or college statistics, we have only 8 samples here, so our statistical power is very limited. If you're doing research and you have more than 8 samples, your results will probably be more powerful. What DESeq does is it's a standard method for differential expression in bulk RNA-seq, and it uses a statistical model to test each gene's expression and how it differs significantly between 2 groups. And it'll produce a results data frame that has the average expression across all samples. In our case, higher will indicate that that gene is more expressed, lower will be less expressed. The log to fold change. Once again, a positive log fold change will mean that it is higher in ALS. Negative means it is lower in ALS if you're comparing ALS versus control. And a p-adjusted value. And we will use, and you can set also the significance threshold for this p-value. This cell kernel will run DESeq2. And I can go over, some of the thresholds, and you can change them as explained. So we will have our counts matrix. We will set a threshold. ALS versus control will be 0.1. If you want to be more stringent, you can change it to 0.5. It'll filter the genes. In our case, we are also filtering genes with a count greater than or more than at least 10 in at least 2 samples. And this cell, should you choose to run it, is motor neuron versus iPSC. To be cognizant and aware of time, this step does take about 4 to 5 minutes to complete. So if you have been running along with me, I'm just going to pause the run along and show you what the outputs look like in the HTML if you would like to go back and complete the steps yourself. So I'm going to navigate in the outputs file that has the the HTML file that has the outputs to our DESeq. So you can see that it'll do the filtering, it'll do the primary comparison, and it'll produce this data frame that has the log fold change, our mean base, and our statistical p-values and adjusted p-values, and it'll tell you what your significant threshold is. And we can see that from this analysis, we'll have about 8,000 that seems to be higher expressed in ALS genes in the motor neurons and about 8,321 in the iPSC cells. There is an additional kernel that I have set to allow you to do ALS versus control without differentiating between the cell types. We can then run a kernel to save our results as a CSV file to that output directory. And we will then generate something called volcano plots. And this is a standard way to visualize these differential expression results. Each dot will represent a gene, and you will see that there are two axes. There's an x-axis with the log-fold change. So the more positive or less negative will determine where on the graph it sits. On the x-axis, our y-axis is our statistical confidence. So higher on the y-axis means that it'll be more significant. And we have also colored them. So gray genes will be not significant, red will be significantly upregulated in ALS, and blue will be significantly downregulated in an ALS. Again, you can change the gene, you can change if you're looking at ALS. That is up to you. So this is an example of our volcano plot for the first analysis that we did. We can see that we have a large number of iPSC cells that are higher upregulated and a large number there that are downregulated. We can then run a few cells to produce a summary, and it'll generate a summary saying the top upregulated genes. Right now this is 20. You can change that to more or less if you wish, as well as the downregulated and a summary. There's also a gene category analysis. So if you have a specific cell type that you're looking at, whether it's causal genes, motor neuron markers, stem cell markers, you can go ahead and set that and see which genes are up or down regulated or statistically significant in this analysis that you are doing. There are a few cells here. We can then produce a summary of the plots and the files that we have generated and a few key findings to investigate. If you would be interested in doing that, you can go ahead and do that analysis yourself. Once again, this notebook is available to you. Once you have Workbench access and you have been able to duplicate this workspace, feel free to, you have created a copy in the repos folder, so feel free to go ahead and play around with those notebooks with different data sets, different genes. It's all up to you from here.
Yeah, so I just like to highlight that for the sake of time, we chose to use data from our stem cell core, which again, we have a few cell lines. It's a growing data collection, but just for the demo purposes, we chose that data set because it's small, but I just want to highlight that to mention to just take the results of this demo script with a grain of salt because it is underpowered. With that, we will go into a verbal Q&A mode. So yeah, please feel free to raise your hand if you have a question and we'll give you the floor to speak.
I saw many people had trouble with the access at the beginning for the workspace. I mean, how can we get the access? And I just want to revisit by looking at the video after finishing this session. But without this access, I don't think we can do much of anything. Yeah.
Yeah, absolutely. I think the reason for the issue was prior to this workshop, based on the email addresses that were used during registration, we gave access to users in this workspace or in this workshop to a specific pod building information within Verily Workbench. So I suspect that that was the reason why some people had trouble because when some people provided a certain email address during registration and then use a different email address to access the data engine. So moving forward, for those of you who you used a different email address to apply for access, you'll have to go through the steps that again are outlined within the user manual within the data engine. Also within Verily Workbench has some documentation page. So I would suggest going through those resources. There should be pretty clear instructions on how to link billing information to the email address that you use to gain access to the data portal. Once those steps have been completed, you shouldn't have problems. Emma?
So I think there may be another issue is I agree with all that, Daniel. However, I think 38 of the attendees did not have access to Workbench, which suggests to me that they wouldn't have had access to the the data engine either. Because I think our process is typically that a user must reach out to Target ALS through the Google form that's linked on the Target ALS website. Then once that user gets vetted and approved by Target ALS, they are then granted access to both the data engine and to Workbench. So it suggests to me that I think you're right that some people may have experienced using a different email than the one that they used to access Workbench. But if you have no access to Workbench, then the issue is actually that you need to go through the process and sign the data use agreement with Target ALS to get access to the data.
Right. And I think
We're
it's worth
happy to send out a follow-up email with a link of how to do that.
Yeah, and another thing to add here is that to get access to the data portal, there's two options. You can gain access through a Google-backed email address or through a Microsoft-backed email address. So that will gain access to the data portal itself. But if you want to download the data off the data portal, as I showed you, or work with the data in Verily Workbench, you will need to have a Google-backed email address. So some users today may have gained access to the data portal through a Microsoft-backed email address and then encountered issues gaining access to Verily. So for those of you who are primarily interested in the tabular data in the data portal, it's sufficient just to have a Microsoft-backed account. But if you do want to download or work with the data in Verily, you will need to have a Google-backed account. And there are instructions in DNAstack's documentation on how to link your institutional email address to Google. If you encounter any issues there, another option is to use your personal Gmail address and see if your institution would be willing to link their billing information to your personal Gmail address. That's a workaround that some users have had success with. Are there any other questions?
I had this is you may have already answered this previously, but in the poll it showed that there are different suggestions for pipelines, and some had to do with genotype to genotype or genotype to phenotype, and also TDP43 aggregates. And when on the Target ALS data engine, those are not necessarily columns that are coming up in terms of the file type and whatnot. And I was wondering if we need to go into Workbench to be able to query those things within the data set, or if you're able to do that within the Target ALS data portal itself.
Yeah, so for some of our collections, we've captured clinical reports of variant statuses. So for a limited set of genes, we have clinical data about variant status. We're also in the process of updating our variant annotations table for all of the collections, and those should be ingested into the data engine within a few weeks. And once those are live, there's a more exhaustive list of ALS-associated genes that you can filter for variants within. And so those will be found within the whole genome sequencing metadata table. There will be a column called ALS-associated genomic variants, and you should be able to filter data there.
Okay, thank you.
Yeah. Any other questions?
I wanted to point out that in Workbench, we support Cromwell workflows, and we have on our roadmap also Nextflow workflow support. So if you're a person that likes to run workflows, that's also supported in Workbench. Within the scope of today's webinar, we did not cover all of that, but you can find out more in our documentation, which is public. Just that Kaya's question reminded me of that in case that is of interest.
Yeah, I guess we can end there just for the sake of time. So let me just wrap up by saying I wanted to briefly reinforce a few key points. First, as we discussed at the beginning, the challenge in ALS research today isn't really access to the data, it's how effectively we can integrate and use it. So what you've seen today is how the Target ALS Data Engine is designed to help reduce that gap and make multimodal analysis more scalable and accessible. Second, you now have a starting point. The workflows, datasets, and workspaces we walked through today are meant to be reused and adapted. So whether that's exploring new hypotheses, validating findings, or extending analyses in your own work, we encourage you to spend some time exploring the portal, revisiting the workspace, and trying to apply these approaches to your own research questions. Importantly, this is ongoing. We'll be sharing documentation resources and, again, the workshop recording. So we're very interested in your feedback. This will directly shape how we improve both the platform and future sessions like this. So after the workshop, we'll be emailing out a brief survey to everyone here. So please do take the time to fill that out and send it back. And finally, we're really excited to see what comes out of all of this. There's a huge opportunity here, and we're looking forward to supporting your work and all that you're doing. So thanks again for your time, and please don't hesitate to reach out by email if you run into any technical issues moving forward. So yeah, thank you guys all for joining.